Hello guys, welcome to another video on my channel, the second one, and it's also part 2 of my Z80 series. And in this video it will be all about this new board for my Z80 computer, this completely new module. And this module serves only one purpose, or it serves multiple purposes, but one main purpose, and this is to add the ability to output sound on my Z80 computer using an FM chip YM2612 and a PSG, and also to provide MIDI input-output. In this video I will go through the schematics of this PCB, as you will see soon. I will try to do some troubleshooting because of this part of the circuit, which will, spoiler alert, not work at all. But you can watch me like half an hour trying to figure out why it does not work. If you want to skip that, please look in the video description, there you'll find some timestamps. And yeah, I hope you enjoy it, and let's get started and I'll show you what we are dealing with. So the main purpose is to provide sound from 3 different sound generator modules. The first one is the 2612, the YM2612, fantastic FM sound generator. The second one is the SN76489, and the third one is the AY-3-8910. Those sound signals are then mixed by an op-amp TL072, or TL074 to be exact, into a single stereo sound signal, which can be switched to mono using a single switch on the front. Those outputs are then forwarded or outputted through 2 RCA jacks on the front of the PCB. The module itself also contains an SIO IC, which provides 2 independent MIDI I/O ports. Since the AY-3-8910 is not only a programmable sound generator, but also has 16 I/O ports, I do use the remaining unused I/O ports to provide 4 trigger outputs or to receive 4 trigger inputs from a modular synthesizer. Since I want to be able to play back sounds and music from different regions, I need to be able to control the clock frequency of the sound generators. To be able to do this, I decided to use a more modern part in this build, which is an SI5351. This chip is controlled via I2C and has 3 independent clock outputs, which can be programmed to pretty much any frequency you want or need. Right here you can see a small block diagram that I tried to draw. On the left you can see the backplane, which connects to the Z80 bus, or the backplane connector to be correct, which then goes through some buffers to put a little bit less stress on the CPU bus, which then goes to the 3 sound generators and to the SIO IC. The 3 sound generators are mixed together in a stereo signal, which is then outputted through 2 RCA jacks. The SIO is also connected to the buffer and has a clock signal, which comes from a 1 MHz crystal or 1 MHz quartz oscillator, which is divided down to 31.250 MHz. The 3 sound generators are provided with a clock signal from an SI5351, which is controlled via I2C. Right here you can see the schematics of the revision 0 board that we are building in this video. You can see right down here the backplane connector, including the bus buffers. Right here you can see a 74HC688, which is the first part of the address decoding circuitry. The address decoding circuitry is a bit interesting because it allows you to set an offset address via jumper J6, and if this offset address matches address pins A4 to A7, and IO request is selected, it then activates the 74HC138, which then decodes the A2 and A3 signals to the individual ICs and generates the chip select signals for the SIO, the YM2612, the SN programmable sound generator, and the other one, the AY-3-8910. And it also generates a buffer direction signal for this data buffer to change direction if you want to read, for example, from one of those ICs. Right here in this part of the circuit, you see the clock generation for the MIDI signal, which is basically a 1 megahertz clock, and a sound for HC590, which is a counter which is used to divide the signal down by 32, and then provides the clock signals to the MIDI SIO. The MIDI input signals are isolated via optocouplers right here up to spec, and the MIDI I/O signals use buffers to resistor networks or resistors to limit the current that goes out and protect the SIO pins on the output pins on the SIO. One special thing about the MIDI circuit is that port 1 has the ability to have a MIDI through configurable electronically. You can select whether the output of pin 1 is the TX pin from the SIO or directly mirrors the input of port 1 MIDI in, this one right here. And this is useful when you want to daisy chain multiple instruments, and when, for example, reading this and then resending it via CPU would add too much latency. Since the board is way too small to allow multiple MIDI I/O ports, I've decided to use a DB15 connector and then build a breakout cable for that. Right, yeah, for that. Okay, then there are the sound generator chips themselves, the SN76489, the YM2612, and the AY-3-8910. And these are all generate individual signals, which are then mixed together. The only issue that one issue that I faced here is that the old chips generated different outputs. For example, the YM2612 had a stereo output, the SN76489 has a mono output, and the AY-3-8910 has 3 individual outputs. And then I decided to build a stereo amplifier or mixer circuit right here using standard op amps TL074s and mix the signals together. The mono signal from the SN76489 is mixed onto left and right equally. The YM2612 is directly mixed onto left and right, and the AY-3-8910 mixes channel A to the left channel, channel C to the right channel, and channel B to both channels. And therefore, I can generate a stereo signal. If I don't have the ability to play back stereo or don't want stereo, I can use this switch here to short both channels together and create a mono signal, which is then outputted or can be outputted through both checks simultaneously, and allows me to, for example, use a CRT or a monitor which only has a mono input. For the voltage supply, I have some linear regulators right here, 74L09 and 79L09, which generate symmetric 9 volts plus minus 9 volt power supply for the op amps, and also some Farad beats which filter the 5 volt supply for the sound generator chips, or for the YM2612 to be exact. Yeah, their AVCC is plus 5 VA. The only 2 things that are left is the clock generation for the sound chips, which is, as already mentioned, this SI5351 right here, which then provides the clock signals to those 3 ICs. As you can already see, there's a mistake which we have to fix in this video, and this is that pin 3 and pin 4 are swapped in this revision. Right down here, since those are 3.3 volt signals and not 5 volt signals, I thought it would be a smart idea to add those level shifters. Unfortunately, as it will turn out in this video, those won't work at the desired frequencies, will cause a lot of pain, and I'll end up, spoiler alert, leaving them out. But you can still watch me trying to troubleshoot the circuit and trying to come to a conclusion. There are some circuits in the internet which I already found which are using those outputs from the SI5351 directly, because 0 volts to 3.3 volts is still enough for TTL logic levels, or at least I read that. and yeah, we will see in the next part. The AY-3-8910 has, as already mentioned, two 16I/O ports, which I decided to use for trigger inputs and outputs for a modular synthesizer. Those are protected by 100 ohm resistors, U74LS125 buffers for the outputs, and the inputs are protected by 5.1 volt Zener diodes on the positive side, and to prevent them from going to the negative side, I added some 1N for 1/4/8, and this should be enough, hopefully. I will test that as well at some point in the future. And that is basically it. That's the entire PCB. The only thing that I didn't mention is these two connectors, which I also won't populate for now. These basically allow me to add additional sound ICs in the future if I want to. And don't have to design a completely new board, only add a small board on top. I can plug in on those two connectors, and then I can add a additional sound chip like a SID, for example, and still use those two outputs, mix it into those two outputs. All right. I already did some stuff to this PCB. I've already added a switch and those two RCA checks. The reason why I already added this is because I also got the footprints wrong. Well, technically they are at the correct position, but the diameter of the through holes were too small, and I had to do some modifications to the PCB and to the switch itself. Not too much of a problem because this is only stereo mono. It does not look beautiful if you look from the side, but it works. I've already tested continuity. That's fine. And I soldered on the backplane connector because I already was soldering, and usually I start with the lowest profile components first, for example the IC sockets or the resistors, and then work myself up from there. Now I already have those connected because I was too impatient. My bad, I guess. I'll still be able to assemble this, I think. And so let's get started. I also already have my soldering iron right here, my fume extraction system right here. Let's turn it on. I hope that's okay. Let's see if that works. Because your lungs will thank you later, or not if you don't use one. One thing is that my soldering iron tip of my soldering iron is a bit dirty. I just see there's something inside there. No worries. It's a bit dirty, and I've bought myself those reactivators for soldering tips. I've never used them, or did I? I don't know. Let's put this aside, not burn myself. Let's try again. It at least looks like it does work. I don't know. We'll see. We'll see. Okay, let's put this aside. Start assembling. The first thing that I want to start with is actually this part right here. This section is what I've shown you right here. Let's switch back to a desktop. It is this IC. This one is this connector right here. I have it on a separate module. And those transistors are those right here that are used for level shifting. And before I continue with anything else, I want to assemble this section of the PCB. Test if it works, because if it does not work, I should have tested this before. Yeah, I'll have to find another solution for generating the clock signals. I already have an idea how I'll be able to do this if this won't work. We'll see if this works. That would be great. So let's get started. Alright, I found the back with resistor networks, and right here I have my multimeter set up, my bench multimeter, and my counter, but we're not using this right now. We need this for later. Right now I only need to find one resistor network that's actually suitable, that actually matches the specification. So first of all, let's have a look at some of them. This one says A103G, A104. 104 should be 10K, I guess. So that looks promising. So I guess 104 means 4 zeros, which means 10K. Let's verify that this is true. So this is one that's possibly correct, and this is one. So I'm not sure if this means 10 with 4 zeros or 1 with 4 zeros. I'm pretty sure that this means that it has 4 resistors with one side, with one common side, which is most likely the pin with the dot. We can check this when I take my leads and connect them to one side, and let's say connect them to this one. So yeah, this means 10 with 4 zeros. You can see it's 100K. So that would mean this is a 10K one. Let's check if this is actually the correct one. You can see each pin has 10K resistance towards this pin. If we now take 2 other pins, measure them, it should be 20K. Yes. So this one is the correct one. I have more of those that I need to find. I have another resistor network right here, which is also 10K. This should also be 10K. I have another one right here. Let's get started. That's actually the part that I'm least looking forward to. It's quite a lot of work. Yeah, let's see how this turns out. So first of all, one thing that I needed to check was the orientation of the pin layout right here, because as I've shown you earlier, I think that I made an error right here. Pin 3 is SDA, but it's actually wired to SCL, and 4 is SCL, which is actually wired to SDA. So now let's check if I actually have to cut those, or if I made 2 mistakes which cancel each other out. So maybe this symbol is wrong. I don't think so. Here is my another bin of parts. So this is the IC. I have V in, ground. 3 is SDA, 4 is SCL. Yeah, unfortunately, no mistake. So, okay, I pulled up the schematics of the multi-IO board right here. This was originally meant as the I2C bus controller PCF85484. This didn't work. I'm now bit-banging it with the BIO. But it still allows me to verify that SCL is A22 and SDA is A23. It's A22, now I already forgot. A22 is SCL serial clock, A22. A22 is SCL, A22 SCL, SDA, yeah, they are absolutely swapped around. So I have to cut the traces and rewire it. I've verified again that the mistake that I spotted earlier on, this one right here, those pins are actually swapped and I need to cut those traces. Now, I want to make absolutely sure that I cut the right traces. So I will have a look at the PCB layout right here and see where those traces are going. These are those two traces, they are on the front layer, so it's actually quite a good idea to cut them before I solder. I'll only cut them now and then later solder the batch wires. Those are those two wires right here. Okay, the traces look like they've been cut. Let me quickly verify that this is actually the case. I've checked with the multimeter right now. So we can actually get started, and I suggest that we start with those resistors. Okay, it looks like I didn't short anything. Just take the solder iron again, just reflow those joints to make sure. I like to use those tools here to make sure that there's actually no solder bridge between those pins. Now let's add the resistor network. Let's check the orientation. I think the point or the common pin goes to the top. Yes, this one goes right here. That's the resistor network. This looks good so far. Let me just add this connector right here. Perfect. So this one, it goes in like this. Yeah, that's correct. This way. I don't like these boards just flipping around, but that's the way it is. Alright. Then this section is already almost done. I want to add a crystal right here and the socket for the clock divider right here. Let me show you what I mean. Those two ICs. This is where's the label? It's U10 and the crystal X1. There it is. X1 and U10. So this one and this one is this one and this one. So I need to get a socket for this and the crystal. I've got my box of crystals. Let's see if I am actually correct. Let's verify that in the schematics. In the schematics it actually says 1 megahertz. Not that I've designed it with 4 megahertz. It says 1 megahertz. Well, technically it would be also okay to use 4 megahertz. Then I only had to forgot to order the part. Okay, I just found out that I don't have 1 megahertz crystal. Not too much of an issue. I will add a socket instead and test with a 4 megahertz crystal. I just have to be aware that I would expect a fourth of the actual frequency that will be displayed later on. This means it will probably... Yeah, I don't want to do the math right now. So, where is pin 1? I've prepared the sockets. Where's pin 1? According to my schematics, pin 1 is right here, which means the notch should be facing the resistor network. This means this orientation looks good. Use my tape again, recycle everything. Yeah, it's looking good. So now I can solder in the rest of the pins. Okay, I actually relocated the camera for you to be able to see what's going on a bit better. Those two sockets are soldered in. This means that I'm pretty good regarding this. So the next thing that I would need to do is to add the botch wires for the SCA and SDL pins for this clock generator right here, and then I'll use an Arduino to test it. Oh, one thing I forgot, decoupling caps for the ACs that are already added. Let me add this capacitor right there. It's not necessary, but yeah, if I'm already working at this part, let's finish it up. I have to buy a second set of these cutter right here of this tool, because this one is awful and the other one is in my tool bag in my car, and I don't want to forget it, so I need to buy a second one for a lab. Alright, that's that. Now let's add the botch wires. I've already cut the traces right here at the beginning, because as you can see it's very tight and would be very difficult to cut them now. So next step is to actually get some wires and hook it up. I like to use this wire wrapping wire. It's very thin, easy to use. I just connect those pins up that need to be connected and glue it, hold it down with some Kapton tape. So I need to connect this pin, A22 SCL is incorrect. That's A23 SDA. So I need to connect some runs down here, them to those two pins. So the bottom right one, A32, is SDA, and this needs to be connected to pin 3 right here. So you will now only see the board again. Right. Yeah, looks fine, I guess. This one peels off. Just has to hold on until the rest is soldered in. This one's not interfering with anything. Let's see which IC I have to use right here. It's the 59074 HC 59074 LS 590. It doesn't really matter. Let's just search for 590. Nothing really. 74 LS. Just found out I also forgot to order the 74 HC 590. I somehow assumed that I had those in storage. Apparently I don't. I usually try to use chips that I have in storage. I don't know why I decided to use the 74HC590. I don't know. Maybe I thought I had it in storage. Maybe I forgot. I mistakenly thought, yeah, I had 595s. I have those. Those are shift registers. Yeah, not the same ICs. So only test this one right here. I'll hook up the power supply, and I will hook up an Arduino and my universal counter and see if I can get clock frequency signals out of here. And I think that's my main goal for today. Okay, I'm ready for a next step, which is to actually test if this is working. For this test setup, I've prepared my bench power supply, my universal counter, and my bench power supply. I can set this up to 5 volt, 500 milliamps. Let's say, I guess that's too much. Let's say 20 milliamps. Oh, that's, I think, the least that I'm able. 0.02 milliamps. Okay. All right. Turn it off. Then let's hook this up. Check the pin out. Backplane connector. So the lower one is ground and the upper one is 5 volts. This means this one is ground. And ground can also be connected to ground. And this one is 5 volts. That's correct. Let's hook up SDA and SCL. SCL is the upper one. All right, now everything is hooked up correctly. I have this lead right here, which goes to my frequency counter. Turn it on and hopefully nothing goes wrong. Nothing is smoking. That's always a good sign. All right, I've got this demo sketch for the SI5351 library from Adafruit loaded. I'll use this for now to just check if this actually works. I later have to implement all this stuff in assembly in my Z80 computer BIOS, or not BIOS, or in the program that I write for audio playback. For now, this will have to do the trick to just verify that the thing works and that the level shifter is actually working. Alright, I made some small modifications to this output to output a more reasonable frequency, hopefully. I don't know what we're supposed to get here. Pin 0 is attached. Looks like it's now 77 megahertz. Okay, let's check. So it looks like it's 77 megahertz. Yeah, check right here. It's not really what I'm looking for. Okay, let's check if this is the correct pin. Yes, clock YM, that's correct. Okay, maybe first check the third clock pin. Clock SN is this one right here. Okay, that's wild. Let me show you. Okay. Okay, now we're grounded. Can remove this one, can remove this, and probe right here. And we see nothing, nothing, nothing. What's going on? Alright, I did some experimentation and I found this website RF0. It has a calculator where you can set your crystal frequency, desired frequency, and it calculates registers, which is very useful when I code my program in assembly later. So maybe I'll just hard code the most used frequencies and yeah, just dump the registers and something like that, I don't know. They also have some code right here which I stealed shamelessly, and I'll upload it. It looks done uploading. Okay, it should only output on channel 1, I guess. There's nothing there. There's something. There's something. I assume maybe that's the issue. Nothing there. There's something there, but it's way too high of a frequency. Looks like what I'm actually calculating here does not work. Okay, I fiddled around with Arduino and I was able to calculate the desired frequency. Let me show you how I did this. First of all, I used this website and I found this article which explains how to insert those values. So this calculates the desired frequency registers that are needed to generate the desired frequency. The values that are important are A, B divided by C, and the output multi-cent divider value D right here. And then I put A into here. A was 24. Then which one is this? Then B is 0.544. So this is 0 and the fraction is right here, 544. And then set up multi-cent, select PLLA, and insert the D value right here, the multiplier. I think it's the multiplier, I don't know, to be honest. E right here, and yeah, that's it. And now I have a signal right here that is, if we go a bit closer, 7 point something megahertz. The issue with the oscilloscope is that it's not really accurate, so let me measure it with my universal counter. Or before I set it up differently, let's check if this value is actually outputted right here. I guess it was. No. Third one. Okay. It seems like I made some soldering error, because right here should be a signal. At this side of the resistor there is, at this side it's not. It's not getting hot. But I verified that channel 3 is working. Okay, there's not 5 volts right here. And there should be, or should be ground, I guess. Oh, yeah, that's the output. That's the output right here. Those are 5 volts because it's not pulled down. This is the control signal, which is, I don't know, wrong. This is ground. And I assume that there's a bridge, some solder. Right. The only reasonable explanation is that there's some short. There's a short to ground. Okay, let's verify that. This is an isolated issue by setting up the other outputs as well to the same frequency. Okay. Interesting. They have the same issue. As if it's I don't understand, to be honest, what's going on. Let's set up the last one to be 10 kilohertz. see if it's dependent on the frequency. Yeah, there you can see this is working. Okay, I made some changes. I changed channel 1 to 10 kilohertz. Let's see if this made a difference. And it did. So, interesting. So I thought that the 2N3904 would be capable of switching frequencies up to 100 megahertz. At least that's what I read in the datasheet. Datasheets right here. Transition frequency 300 megahertz, 10 milliamps, 100 megahertz. I'm not that experienced with this kind of stuff. As you might have guessed, you might already know the answer. You know what I'll do? I'll try swap out the base resistor for something smaller, let's say 100 megahertz, and try again. Maybe this might be the issue, that 1K is just too much for 8 megahertz. I don't know. Let's see if this is the problem. There is something, at least. It makes some kind of difference. But not the amount that I would like to see. Okay, let's just try and solder it. See what happens. Well, doesn't really look like it worked. It did work. Well, wait. We have to reinitialize it. I bumped it in a way. Yes. You see, there's quite a difference. But at least right here. Just the input, that's the output. There is at least something. I have to find another solution. I don't want to make a new PCB. That was the thing that I was least worried about. I thought that this would work, because you see it does work with frequencies below 10 kilohertz. It does work with 10 kilohertz, but it doesn't work with 7.67 megahertz. Which is disappointing, and now I have to think about another solution. I'll be back once I have another idea. Alright, as you can see, I did some experimentation with LT Spice. I realized that I understand far less about transistors than I thought that I would. And I still don't know why it works now, or it seems to work now. I'll give you my best try on explaining why I think it happens, or what I researched so far, or discovered by experimenting so far. One of the main changes that I did was changing this resistor right here from 10K to 1K. But in theory, it should also work with 10K. Yeah, it only changes the form of the clock signal a bit. So it should not be necessary to change this right now. Here's a load that I've added to simulate the TTL chips. I've changed it a bit. Now it's 16 milliamps. I don't think we'll draw that much. Let's say 800 ohms. Then we have around 6 milliamps. And this waveform looks good enough in my opinion. One of the main changes, and pretty much the only change that I guess we need to do, is edit R3. Because if we take a look at the voltage at the base of the transistor, if we remove this, you can see this looks exactly what we saw earlier on the oscilloscope. It won't go low enough to turn the transistor off. And my assumption is that this is caused by the capacitance on the collector, between collector and emitter of the transistor. I'm not sure right now, this is not educational, so if you know for sure, let me know if this might actually be the problem. I did some research and I found out that you should not drive those transistors into saturation at higher currents. I tried out using Schottky diodes right here and there. Did not work exactly the way I wanted it to. It made some improvement, but not as much as just adding this resistor right here. And this resistor is actually builds a voltage divider which reduces the voltage that is then present at the base of the transistor, but it also provides a path for the current to sink through the transistor to ground. And because this source right here in the datasheet only allows up to 8 milliamps of output current. I don't know if this is still too much. I don't think so. I think this should work with the 1K resistor right here. This chip should be safe. And you can see the voltages right here actually go down to 0 volts. They actually drop right here. Let's go back. If we, for example, take the input signal and then the signal right here, you can see it rises with the input signal and then drops right here at this point, but it doesn't drop to 0 volts. And this is a point where I still don't understand what's going on, because apparently there's still some current after turning it off that flows through the collector to the base and then through this resistor to ground, which then slowly decreases until 0 volts. And then at this point, at some time, the input becomes high again, 3.3 volts again, and this complete cycle continues. So I still don't fully understand why it's working now. I learned that you have to take much more consideration to designing your circuits when you run them at 10 megahertz or higher frequencies. In this case, this seems to work good enough, and I'll try to in this case, I think this works good enough, and I will try to rebuild this or add this transistor to the circuit and see if this actually fixes the problem, even with the 10K resistor network. And if it still won't fix it, I will change this resistor network right here. For example, we can remove this right here. Now we would have the situation that we have after adding the resistor, and it won't work. Yeah. Only if I change this to 1K, we get some sort of usable waveform. Okay. Still don't know. I still don't fully understand why this works, but seems like it will. And I have to do a lot more research and learning about transistors in the future. For now, let's try this out. Let's see. So what I'm about to do is to swap this one out with a 1K resistor network and to add a 330 ohm resistor to ground for all those collector pins of those transistors, and then see if this makes it work, or if it doesn't and I have to abandon this idea after all. Alright, the first one is soldered. Before I do all the rest, I just want to check that this actually is the solution. So let's plug this in. There you see the current waveform. This is 236 kilohertz. It's not the frequency that I want. .35. Interesting. As you can see, I've added this 1K resistors. It's not beautiful, but at least now I would have, if I haven't removed this right now, reset it. There are my waveforms. Now check it at the output, at the resistor. So all 3 outputs are working. I'm not sure yet if those voltage levels, there it is, are good enough for TTL. So unfortunately you can't see it on screen, but on my scope window, on my scope itself, it says the minimum voltage is 1.2 volts and the maximum voltage is 3.37 volts. Let me just look it up. It's not what I wanted. Yeah, I wanted 0 to 5 volts, but maybe it's not very much better than the clock chip itself. So if this is enough, maybe I could just bypass it, and this would also be enough. So this whole circuit would be unnecessary. And if I redesign the board, which is very likely, I will use 74HCT gates to buffer it and convert it to 5 volt TTL signal levels. So TTL voltage levels. Low is between 0 and 0.8 volts. High is between 2 and 5 volts. So 0.8, which is bad because it won't go down to 0.8. It's still not doing what I wanted to, and I guess for now I will just abandon this idea, use the voltage level directly out of the SI5351, or connect the outputs directly to the TTL inputs of those sound ICs, because the voltage levels should match high and low. And in the next board revision I'll probably use 74HCT04s to buffer those clock lines, clock signals, and yeah, then it's fine. Fixing this is just not worth it right now. If it won't work without those, I don't know, maybe I have to yeah, if it won't work without those, I guess I have to find another solution, but that's a problem for the future. For now I'll just unsolder those transistors, everything right here, and just connect batch wires directly from here, from those resistors to this resistor network. I guess that's that. Alright. Alright. So far, so good. There's the signal. And at this one, this is the 74HC590, which serves as a clock divider, and then I have to find the other part. This is the crystal. Okay, that's in there. Nope, this won't work. Have to trim those legs a bit. But I can still check if the frequency is correct. Nothing. Okay. 11 and 13 should be the corresponding inputs. So this is the third pin from here. There's a 1 megahertz clock. And then output is supposed to be pin 4, right? Oh, there's the signal. Yeah, that's what it's supposed to do. 31.250. I hope I calculate this correctly. Otherwise, I can easily fix this by using the other outputs. So this part is working. Nice. At least something. Okay. Now it fits. Perfect. It turns out that sometimes the solution is much simpler than it's supposed to be, or that you think it is. By just bypassing those level shifter transistor stuff that I thought that would be a good idea. By bypassing those, we get the clock signals at the corresponding pins. The clock generator for the SIO that preserves the MIDI ports is working. So, only thing left is to populate the rest of the board, and I'll show you a small time lapse. it's done. It's been a few hours, and was quite a lot of work to solder all those components and sockets to the board. I struggled, for example, with the diodes because I chose the wrong footprint again. I swapped some parts around. For example, these two capacitors are a bit smaller than specified, and those are a bit bigger, and that shouldn't be an issue. It's just that those 2.2 nanofarad capacitors that I originally chose have this footprint, and they won't fit here. But I don't think this will be an issue at all. Those are decoupling capacitors. I think 10 nanofarads is still low enough for not to have an effect on the sound. We'll see later. Okay, the last thing that I'll do today is to populate the board, and then tomorrow, hopefully, give it a try. Start it up, plug it into the computer, and see if I can talk to the chips and do cool stuff. Alright, the biggest part of this video is done, which is assembling this thing. In the next video I will try to get this to work. For now I'll just give you a short right to left overview of what this thing does. Starting on the right, I have the bus connector right here, the backplane connector, bus transceiver ICs for buffering the bus, so not all ICs are connected to the bus, and the CPU doesn't have to drive them all. I have some logic chips right here for address decoding and stuff like that. 74HC688, which does the address decoding, so I can set an address for this card. It's the upper 4 bits, and the rest is then decoded by the 74HC138. Then I have an SIO in conjunction with this oscillator and the counter below this. It generates a clock for a MIDI signal, and this serves the MIDI port right here. And those ICs, those optocouplers right here, and this, I guess, those two ICs here do support them. Yes. Then right here is the first sound IC. It's an AY-3-8910A. The second sound IC is an YM2612, and this is an, I can't read it right here, give me a moment, an SN76489 AN. Then right here is the analog section. I can mix all those channels together into a stereo signal, or with this switch it to mono. There's the amplifier for the output and RCA output jacks. There's a voltage supply for the analog section, so it doesn't use the same supply for all the digital stuff. And this section right here uses the remaining I/O ports of the AY-3-8910A to provide or to receive trigger signals from a modular synthesizer. not used yet. I haven't finished this project yet, so I can't test this, but I actually plan on using this computer in combination with my modular synthesizer. Yeah. I hope you enjoyed watching me building this thing, fixing the error with the clock generator or trying to fix it. And you got some insight in how this thing works or how this process works, because this is not a unique case. I go through this process with every one of my PCBs. There are issues. I'm not perfect. I'm not that experienced with this stuff. I still make mistakes designing these things. And then I try to fix them. And this is what this is about. This project is about learning, gaining experience. For example, learning that you can't drive transistors at 10 megahertz without any additional circuitry, or you can drive them out of the box at 10 megahertz with just one resistor, and that's it. Apparently, I learned that I have to do some research on transistors and how they work more in depth for the next project. And hopefully there are still some things that I learned from this project. For example, programming those devices. Hopefully not fixing this analog section because it will work out of the box. We will see. And yeah, this is what this is about: learning, having fun, and trying to understand how computers work. Hope this was interesting to you. Hope you had fun watching this. If you have any comments, any resources on learning, on the issues that I had, or any ideas or things that you saw, feel free to write in the comments. I'd love to learn more and get better at this. And yeah, if you want to learn more about this, you can check out my GitHub project. There's a link in the description, and on my website there are some resources to this computer, or watch the first video. Until then, have a nice time and see you in the next video. Bye.